We're doing a series of videos on the SLS Mindset, selective laser sintering, how to design for this special production-ready polymer additive manufacturing process. I'm Pete Zelinski. I am at Lifestyle Additive, and I am with Nate Stevens, Director of Operations.
Hello,
Hey,
happy to be here.
I'm happy to be here as well. Thanks for having me. So, SLS, it is a precision additive manufacturing process. It is specially suited to doing fine details. We're going to talk about that, how to realize that precision, but first let's deal with an assumption that's out there, the assumption that 3D printing in general is not a precise process. So how do we think about SLS in the context of that assumption?
Yeah, so I think most people already have a misconception around 3D printing with it being associated with more desktop printers and prototype level printers. And the way I describe SLS is it's the difference between a laser printer and a inkjet printer. And what that allows is the laser can be much more precise in sintering exactly where we want it to be, and it can be adjusted for individual applications. So we can fine-tune the laser settings to give you exactly what you need versus it's kind of you get what you get.
So in that fine-tuning, for example, what becomes realistic? How do you talk about the kinds of features or the kinds of precisions you're able to realize?
I tell people when they bring me their parts, default tolerancing is about plus or minus 10 thousandths of an inch. But if we go through a few iterations and really finely tune the laser to that part specifically, we can get under plus or minus 5 thousandths of an inch, which is even at a machining level, CNC machining level is very precise. For 3D printing is ridiculously precise.
And is that precision and that control over precision the same in XY as it is in Z?
No, it is not. And part of that is because of the process itself. All additive manufacturing relies on a layer by layer buildup of your part. And so we're really only able to control the precision in the XY plane, parallel to the build frame. The Z plane is just where the layers line up. We try to maximize the most critical dimensions being located in that XY plane and the least critical dimensions being located in the Z plane. The Z is more on the plus or minus 15 thousandths of an inch.
So these are fine detail components so that orientation figured in an important way to the precision that you achieved.
Yeah, these long skinny parts, they were built like this so that that circle is in the XY plane, and it gives us the most accurate circle. If we printed them flat, they would not be circles anymore. They wouldn't go together.
Another part of the XY precision is the snap fit you were able to get.
Yes, so we're trying to control the widths on these snap features. We've gone through a couple of iterations, but this one actually works really nicely, so we're gonna keep that one.
There was another snap fit problem you solved by working with your customer to alter the dimensions of a detail to align with layer increments. How the Z height layers can actually be used for precision as well.
Yeah, one of the limitations is when a feature lands between layers, the printer will always default to adding material. If you design something that's gonna land in that Z orientation and not be perfectly distanced, it's not going to fit. And so I either advise them to take a little bit off or dimensioning their part in layer increments so that it allows their part to be built exactly as they intend it to.
That snap feature ended exactly where a layer line happened.
And we were able to get that result repeatedly for 50 plus parts.
Are there material differences? Are some materials more forgiving of precision than others are?
It's about understanding the material, it's about understanding the machine, it's about understanding the software. Most engineers can't be expected to understand every little detail. That's my job. We adapt their parts to fit in that process so we can get an expected result. We just ran some parts in a glass-filled material and it behaved very differently. We learned a lot. That's what we do. We learn what we can so that we can transfer our knowledge to the customer.
And the figuring it out, there's a lot you can do all in one build.
Yeah, this is a part where we're testing a few different laser settings. We are able to capture all of it in one part and iterate quickly and find, okay, this is the one that behaved the way that we want. Now that's what we're going to translate to the actual parts.
SLS is a very repeatable process.
Correct. We promise repeatable results with every build. Doing exercises like this allows us to have a high level of confidence.
Can you give me one or two just concrete design tactics?
First things I look at is how are the different components in an assembly interacting? I will give the parts that kind of standard tolerancing. If that works, then problem solved, we move on. The next thing I think about is orientation. Kind of have to prioritize which one you want to be the most accurate.
You might play with the angle,
Share the accuracy
yeah.
with all the features. So sometimes that doesn't necessarily optimize the nesting, but if it gives us the best result, then it's what we have to do.
So when a customer says, we need tighter tolerances,
I'll go through a technical drawing, identify critical dimensions. We'll start by orienting those in the XY plane. Most of it comes down to communication. Technical drawings are the best way to communicate to us. We might not be able to get that feature exactly the way we want it. We build a little extra material so we can remove it. We start working together on what steps need to happen before printing and after printing to give the best result repeatably.
This episode's part of a collection on the SLS Mindset, how to design for selective laser sintering. Check out other videos in this series.